Hello everyone. So today we will discuss a problem related to group theory, and this question asked in everywhere, almost everywhere in PhD interview. So to discuss this question, okay. First, the question is very interesting. Okay, the question is very interesting and very uh, powerful thing that tells something to element can be factorized in some two elements of it, some subsets. Okay, so let me start with that question and we will discuss the question in very detail. Okay, the question solution is very easy. So first I have to uh, read the question or what the question says. Okay, so first the question says that let G be a group. Okay, G be a group which is a finite group, means its cardinality is finite. So we can talk about how many elements are there. Okay, first of all, that let G be a finite group. Okay, and S be a subset of G. S a subset of G. Okay, means it is a subset. So since G is finite, so every subset has to be some finite. Why? You know something because cardinality of S is at most could be the cardinality of G, right? That. So what are the description given by the set S? The description is that contains more than half of the elements of G. It contains more than half of the element. Means if G has n element, then S has at least n by 2 elements. At least n by 2. Okay, n by 2 need not be integer, but mm, so it has at least n by 2 elements. Okay, then then I have to show that every element of G can be expressed in the form whatever element you take from that group G. Okay, that can be in the form in S1 and S2, where S1 or S2 belongs to S. Okay, is the question is clear? I'm explaining the question again. Okay, this is very important question, and this question asked in almost most of the places in either Pune, IIT Kanpur interview, and everywhere almost, and everywhere. So this question is very interesting. Okay, so let means I have given a finite group and I have given a subset. Okay, which is cardinality at least the cardinality of G divided by 2. Okay, then what I have to show that the G, every element of G, whatever element you take from the G, that can be expressed in the form product of two elements of that subset. Okay, so now let me begin with the proofs and how should I approach that question. Okay, since I have to use the finiteness of G. Okay, so we will use that finiteness. Suppose let uh, order of G is n, okay, which is finite, clear, which is finite, okay. The n is a finite number, and this is order of G. So, okay, I just have to write that it will be clear. Let cardinality of G is n, which is finite, okay, and cardinality of S is k, which is also finite, okay, and by given condition k is greater than equal to n by 2 elements, more than half of the elements, more than. So we can just eliminate the equal to. So more than half of the, more than, okay, half of the elements, it's n by 2. Okay, so suppose that it has k elements, so let just name the set. Okay, that name that set is, okay, that name that set, it has k elements. So just I am defining int let is as k element is 1, is 2, is k. Okay. And what I have to show that whatever element I can take from that group, okay, that should be written in some product. So I will construct another set with the help of this set is okay. Now how that how will I construct that set? So let, 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 let the take set T. I will set, I will construct another set. Okay. With the help of that given set S. Okay. With the set given set S. So how so? What I have to show that every element of G, so take any element of G belongs to G. What I have to show, it should be written in some product of two elements of S. Okay. So I am considering T as G S1 inverse, G S2 inverse, dot 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 G SK inverse. Okay. Why S1 inverse, S2 inverse, SK inverse exist? Because S1 is a S1 is an element of the group. Okay. So it inverse must be there. S1 inverse. Okay. I am not saying that S1 inverse should belong to S. I'm not claiming that because that that may not be true because S is not a subgroup. One thing is given that S is only subset. Okay, we are not dealing with more properties of S. So we just need the set. I'm just saying that S1 inverse exists in G. That not necessarily exist in S. Okay, we have to just, but we are forming that from T. Okay, okay. So and S has and T has also these are distinct element. Why these are distinct element? Because every set has in its distinct element. So in S there are k elements. So k are by definition of sets that these are k are distinct. So I have to ensure that this becomes these are distinct. So suppose for some G S I inverse is equal to G S J inverse for some I and J for some I and J. Okay. So by since G is a group element, so its inverses exist. By left cancellation law, what can I show that SI inverse equal to SD inverse? Again, this property holds in groups, so inverse exists. So from there we are taking SI equal to SJ because A inverse is A for every A in G. Okay, in a group where G is a group. Okay, this property holds. So from that, we are concluding that it can't be possible. If two elements are same, then S1 S2 same. So by contrapositive statement, this would imply Si not equal to Sj implies Si not equal to Sj implies Gs inverse R not equal to Gsj inverse. Okay, so that collection we are treating there, it has these are distinct elements. Okay, now T has also how many elements? K elements. So by the last slide consideration, the cardinality of T is greater than n by 2. Okay, now think thinking about that. The S has in more than n by 2 elements. T has more than n by 2 elements. Uh, so these two set must have as element in common. Okay, that means my claim is that that S and T it is always non-empty. This is non-empty. When their intersection must have the non-empty. Okay. Suppose suppose it's empty. Suppose my claim is that their intersection is non-empty. Let suppose on contrary. Uh, suppose suppose on contrary S intersection T is phi. Okay. Now let S is a subset of the group. Okay. T is also subset of the group. Why? Because G is a group, so S1 is an element of G, so S1 inverse also belongs to the G. G belongs to G, so G S1 inverse also belongs to G by closure property. So this is trivial, right? S is a subset of G and T is a subset of G. So from this we can conclude that S1 union T is also subset of G. Okay. T. Now cardinality of S1 union S2 is what it is that it is less than equal to cardinality of G. And what we have we have assumed that cardinality of G is n. And from here we can say that cardinality by cardinality formula for S1, cardinality of S plus cardinality of T minus cardinality of S intersection T less than equal to n. Okay. Now, since S intersection T, we have assumed that their cardinality is there is no element in between them. So the cardinality is 0. So from here we get the cardinality of S plus cardinality of T, okay, minus 0 is less than equal to n. Now come to the point that cardinality of S plus cardinality of T less than equal to n. And what we know that cardinality of S greater than n by 2 by hypothesis, we have proved that cardinality of T is same as cardinality of S. So we can always that cardinality of T is greater than n by 2. So from there, it is clear that cardinality of S plus cardinality of T is greater than n. Okay, and from that we consider that cardinality of S plus cardinality is less than equal to n. So we have not done any calculative error, right? So some error is happening. Why that error comes? Because of a contradiction come because of we have assumed our assumption is false. Okay, we assume something wrong. Okay, so S intersection T is phi. So it can't be possible. So our claim is verified. So S intersection T has to be some element in common. Okay, some element in common. Okay, now we are most of the proof. So we have shown that S intersection T must have node-empty element. What do we know where S is? S1, S2, dot dot dot, Sk. Okay, and T is G, S1 inverse, G, S2 inverse, dot 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 dot, G, Sk inverse. Okay, G, so there is some element common. So some element common means G, Si inverse is equal to some element of G, Gsj. So from where can get so from we get G is equal to Sj Si. Okay, where Si and Sj are elements of S. Okay, clear? So we have shown that G was arbitrary element or in our assumption. Since G belongs to G was arbitrary, so our proof is done. Okay. Okay. So we have done that. So let me rewind the question again. What the question is there? That question is given that every finite group, if S is a subset that contains more than half of the elements of the, then every element of S can be expressed in the form S1 and S2, where S1 and S2 belongs to S. We have shown that small g is Si, where S and Si are belongs to S. So that is indexing is can be you are assumed, right? So what we have to show, what we have done till now, that I have given a group, finite group, and a subset. That subset contains more than the half of the elements of the group. Okay, more than. So that more than is trickier. So that you can verify for any finite group. Okay, you can take Z4 Z4, or you can take D7. Any finite group, we take more than half of the elements. Means you can take D7. Okay, it has 14 elements. Okay, 7 rotations and uh, seven other reflection type elements. Okay, means product of R and S. So if you take all the rotations and one reflection, then we can show that every element can be product of this and these two. It's a suitable choice for two elements. Okay, so that can be done, and the proof is the same for that. What we have done? The G is a group of finite order, so it also has n. Okay, S is the cardinality which has k elements. It takes more than n by 2 elements. Okay, not equal. So then we have shown that suppose it has finitely many elements S1, S2, Sk. So we are construct a new set. Construct a new set. How do we construct a set? We take an arbitrary element G belongs to G. Okay, arbitrary element to G, and construct a new set. So that set, that collection. First of all, we have to show that is collection. That collection G S1 inverse, G S2 inverse, G Sk inverse. Why do we need that? Because we need G equal to Si Sj. Somehow I have to form G Sj inverse equal to Si. So from S, and if I take this set as T, so we have to show that their intersection is non-empty. So from that we can conclude by group theoretic property. Okay, so group theory and set theoretic property. So GSL, suppose it has two elements in common. So then we can say that the S has two elements in common, but that can be possible because S is a set, so it must have distinct elements. So from by contrapositive statement, we have shown that Si not equal to Sj implies GSI inverse not equal to GS inverse. Some properties of group theory needed. Okay, so you can show it easily. Okay, so from that we conclude that S and T has same number of equals. Means you can define a bijective map from that. You can always that map is together. Okay. Now, what our claim is that S and T must have. Our intuition is says that it has more than 5 elements. If a group order is 10, it has more than 5 elements, and we are constructing another set which has also more than 5. So there's these two elements. These two set must have one element common. So that is our intuition. But how do I show that they have more than means one element in at least one element in common. Suppose there is not, then just use the set theoretic property that S union S is a subset of G, T is a subset of G. Their union is that elements of elements means elements of S inverse need not be in S. Okay, that but that must be in G. That's why T is a subset of G. Okay, and that the rest of the calculation are same because their intersection is empty, so the cardinality is 0. So cardinality of S plus cardinality less than equal to n by this is set theoretic property, and by the hypothesis property we are getting that is greater than n. So we are concluding that n less than is n. That can't possible. So this is a contradiction. Okay, so this contradiction happens because of we are considering that their common elements is 5. Okay. From that, we conclude, then just to conclude that the common elements is some there is GSI and this is SJ, so G is SI. Hopefully you enjoyed it and uh, try to say something about your how to like this video. Okay.